Hey, welcome back. Today we're going to be talking about springs in series and springs in parallel for physics and AP Physics classes. So looking at the image on the left here, you can see a mass attached to a wall connected to two springs in series with each other. And when you connect springs in series, that actually weakens the spring constant for the spring system. Let me back up for a moment and write down Hooke's law. So Hooke's law is equal to minus kx, or Hooke's law is equal to minus k delta x, sometimes it's written as. So it just depends. That x represents the displacement from equilibrium position, and the k represents the spring constant. And to understand what the spring constant is, it's useful to think about the units. They're in newtons per meter. So you can have very strong springs, like in cars, you've got very strong springs, like in the shocks of a car. It takes a lot of newtons to be able to compress a spring or stretch it out by a certain distance in terms of meters or centimeters. Typically, a spring constant is measured in newtons per meters. And so if you happen to have a couple springs in series, what that's going to do is weaken the whole spring and allow the compression or the tension to happen, the disturbance of the mass from its equilibrium position with less force. And if you look at it in springs in parallel, it's going to strengthen the spring constant. Okay, so let's work with some values here. Let's just say K1 is going to be equal to 1 Newton per meter, and K2 is going to be equal to 2 newtons per meter, and see what happens with this. And we could say a question like, if you have a force of 10 newtons and you have these two springs either in parallel or in series, what is the displacement that's going to happen? So we could start with this right here, which is Hooke's law. And so minus k delta x, and we're going to solve for delta x. So we're going to say delta x is going to be equal to the restoring force divided by k, and we have to keep our negative sign in there. That's because the force is going to be in the opposite direction of the displacement. So we're going to say, all right, well, what if we have two scenarios? So scenario A and scenario B, and we'll say scenario A is in series and scenario B is in parallel, and just see what happens with these numbers. So for scenario A, you could say delta x for A. We're going to assume minus 10 newtons for both cases, a force of 10 newtons in the negative direction. So now let's figure out what our equivalent K is going to be. So we could say K equivalent for example A. Let's think about this. Our K equivalent is equal to 1 over 1 Newton per meter plus 1 over 2 Newton per meter. And if you do the math here, the answer is not 1.5. It is initially, it's 3/2 over Newton per meters. And notice that's 1 over our answer. So we could say 1 over K equivalent for A is equal to 1.5 over Newton per meter. That's actually not our answer. So we have to take the inverse of that to be able to get our answer, which ends up being 0.66 repeating newtons per meter. That's going to be our equivalent K value, and so we could go ahead and put that in here, 0.667 newtons per meter. And so our displacement is going to be negative 15, or let's just call it 15 meters. That's going to be our answer for A. That's how much this can be displaced with 10 newtons of force. Okay, let's try a similar thing over here, except they're going to be in parallel. I'll pull this over here so we can compare the two and see what happens. If we're going to do the K equivalent for B, remember B is in parallel, and the rule for if they're in parallel, you just essentially add them up in terms of their equivalents. So you could just say, well, that is 1 Newton per meter plus 2 newtons per meter. And so our K equivalence for B is going to be 3 newtons per meter. That's our K equivalent. So we can take what we had done previously, which is this. We had set this up to solve for what our displacement is going to be. We'll use the same exact force, and we're going to say, well, now our equivalent K value is higher. It's 3 newtons per meter. And if we do that, we end up with an answer of 3.33 meters or negative meters, whichever. So you can clearly compare the two, and you can see that with the same force, you're going to get much more stretching out or compressing in if the springs are set up in series, and much less if they're set up in parallel. I want to say two things as I scroll back over here. I want you to take a look at this. This is the opposite. If you're a physics student who is familiar with equivalent resistance problems in dealing with circuits, this is essentially the opposite here. And lastly, I do want to say I've gone over all of the major ideas in high school physics, as well as most of the ideas in AP Physics C Mechanics. So if you have any questions or comments down below, please let me know. And I hope you all have a great day. Take care.